multivariable calculus, but they are particularly important for electricity. And so the first thing that we proved is that for the type of expressions that we have for an electric field that is produced by a superposition of Coulomb charges, and that's basically any generic field, then the curl of that field is equal to 0. So we proved then that the curl of E is equal to 0. Okay, that was one thing. Then from that, and using Stokes' theorem, that was at the end of the last class, from Stokes' theorem, we proved that then, if that's true, then the circulation of the electric field along any closed loop is equal to 0. So this and this are completely equivalent. On any closed path. Okay, so the L or the R, whatever, as long as we move on a path. And then what I was doing is that I was showing that there is a third equivalency, which means that the electric field well, no, what I was saying is that because of this, that there is if we go from point A to point B, whatever, we can consider any closed loop like that and like that. So we go from A to B on the downward path, and we go from B to A on the upward path. And so if we go around this way counterclockwise, then the integral on that curve will be 0. But what we said is that in general, this is true for any line integral, if you have an integral on a curve C from a point P1 to a point P2, something like this, in this case of the electric field, then what is true is that if you, let me call this curve some other letter so that we don't confuse with that one, I don't know, let's call it like that, C. Okay, so, but if you do the same curve integral, but you go now from P2 to P1, then these two integrals have to be opposite to each other. Okay, and the reason for that, that's what I was trying to explain at the very, very end of last class, and then it was late. The reason for that is because as you walk here, the electric field is fixed in space. It's some vector field that depends on position. So in particular, it will take up some values along the curve. And so for example, if I take some generic point on that curve, maybe the electric field will look like that at that particular point. As you walk from P1 to P2, the DL looks like that. And so there is going to be a certain scalar product between the two. Yeah?
Is this only for a constant electric field?
No. No. Good question. Why? Why would it be for a constant electric field?
I'm just trying to think, if you have like one part of electric field like going a direction this way, and the next part going directly the opposite way, and then you, meaning if you take like the E dot dl in the area where just includes one field versus we include both of them, I'm having trouble visualizing.
Okay, that's what I'm trying to do, but no. It is for any absolutely generic electric field, and it's very easy to understand. Okay, let me make the picture bigger, and so this is the curve that I'm talking about. Just doesn't have to be closed, any curve, whatever. Okay, so I go from point P1 to point P2. So the electric field is something that exists in three-dimensional space and is already set by some charges somewhere in space that we created. Okay, so that means that if I go to this point in space, there's going to be a certain electric field, and I draw it. That's at that location, that position, okay? So if I go to this other position, the electric field will be something else. Not necessarily, like you say, constant electric field, could be anything. If I go to this other place, maybe the magnitude is larger and it points in even a different direction, etc. Okay? But that is the electric field all over space. Since we are trying to do an integral on a curve, we really don't care about what happens with the electric field outside that curve. We only care about the values along the curve, okay? So, I'm not gonna first look at the way I walk. I'm just going to try to monitor what the electric field is along the path. So, I start at P1, and the electric field looks like that. Okay? Then I go to the next pixel, and the electric field looks like that. And I go to the next pixel, and the electric field looks like that, etc. Okay? Now the point is that even though the electric field is not constant, not uniform, it is fixed because it is generated by some charges, so it's given. I know the electric field. And so in particular, I know that the electric field along the path. So then I'm going to do the integral. And so what I do is I walk the first step, and the dl is nothing but this vector over here. And then the next step is going to be this vector over here. And the next step is going to be this vector over here. So I divide the curve in 10 pieces, and I have 10 dls. At each pixel, I'm going to evaluate E dot dl. So now for the curve, walking from P1 to P2, the dls are fixed now. And so at this location, I can do the scalar product E dot dl over here. Right? Yeah. And then I do the same thing for the next pixel. E dot dl, and I evaluate it, etc. And I add them up, and I get that integral, right? So to get this minus sign, all you need to realize is that when you walk from P2 to P1, all you do is to switch the dls, right? Because if you walk from here to here, all the dls now point the other direction, and so E dot dl in one case is minus E dot dl in the other.
But in the case where you have the curve that you go from A to B and then B to A in a different way, if the field is not uniform, for example, when you go from A to B, the field could be going parallel and B to A could also go.
Okay, I like the comment, but hold on. Yes, very good comment, but we'll see what happens. So I will come back to that in a second. Okay, that's good. But first thing that we need to realize is this statement. Everybody, now it's good?
Yeah, I was trying to ask more similar to what he was asking.
But hold on a second. I'm first doing one curve to make it clear. Okay, yeah. That's no problem. Okay, wonderful. Okay, now I'm returning to this thing and try to clarify the problems. Okay, so one statement is that this integral is equal to 0 for any curve whatsoever in space. So I take any curve, whatever, I draw it, and that is true because of Stokes' theorem, because of that. So this implies immediately that that integral has to be 0 for all curves. So far, so good, right? Okay. I'm sorry?
What's the connection between those two things? Why is that the field is always curled where you imply that?
Because this thing is equal to 0, then from Stokes' theorem, you have that the line integral of E dot dl is equal to the surface integral of the curl. We proved the Stokes' theorem before. Okay, and because that not only the integral on the surface, but the curl itself is equal to 0, so the integral on the surface is equal to 0, and then Stokes' theorem tells us that this is equal to 0, because this 0 is the surface integral. That's the reason. Okay, so we have that, and okay, so now the argument, hopefully now it will be clear. So this curve C is the closed path, the whole thing. Okay, and in our standard notation, we take it counterclockwise. But since it's 0, it doesn't matter. Okay, so the integral of all this curve is equal to 0. Okay, so now it's a little bit of problem of notation because let me just try to do it with the picture here. So if I take this curve down here, that integral from A to B, okay, so maybe I can do it like this. AB, yeah, doesn't matter. Better to talk about this one. So the bottom curve going from A to B plus the integral on the top part from B to A of E dot dl, of course, is equal to 0, right? Correct? Okay, so what I want to do now is keep the bottom integral from A to B exactly the way it is, but the top one, walk it backwards, meaning from A to B. So it's going to be, again, an integral from A to B, only that is along a different curve. This one is along this curve, and this one is along that curve. Yes? So what happens when I do the integral from A to B? What do I need to do to this sign? That's it. That change in sign is based on this argument over here. Okay? Okay, maybe I would say the same thing in words. This is equal to 0. I would say the same thing in words, just to... The integral over the whole loop is equal to 0. The integral on the bottom from A to B is some value. For example, call it 3. Right? Call it 3. So imagine that the integral is equal to 3. Necessarily, the integral from B to A on top has to be minus 3, because the total integral is equal to 0. So whatever I get at the bottom, I'm going to get at the top negative value. So if I now walk on the top curve backwards, I'm going to get exactly the same value of this one.
Would a way of saying this be that all electric fields are conservative?
Yes, that's the same thing, but that, yeah, it is true. It is true. So do you still have a problem with this? I want to understand.
Is B in the midway point, or is just any general point on the curve? B could be anywhere.
Oh, sure, of course. The issue is, yeah, absolutely. B could be anything, because any curve. Yeah, so I could have done this. I take the curve first. I happen to take the points first. But then I take the point A here and the point B here. I don't care. It could be anywhere. I mean, I took it on the other side, but it could be very close to A. In that case, maybe this will be 0.1, and all this thing around will be minus 0.1, whatever. Okay?
I'm still having trouble visualizing it. If we would imagine, let's say, make it simple, that you have, I don't know, a charged sphere. So inside the sphere, the electric field is 0. Then outside the sphere, you have electric field radiating outwards. So if I draw a curve that on one side goes through the sphere, and on the other side goes around the sphere and connects those 2 points. So don't I have an electric field of 0 on one of them, and on the other one I have a net electric field?
Yeah, but that's a completely different problem, though. We are talking about something.
I don't think any curve, no matter what the formula of the electric field is going to be equal. The integral around the whole curve is 0.
Yep.
I'm just trying to understand, like, just take one simple example where you have electric field in one place and not another place. How that cancels out.
Okay, so, well, I mean, the truth of the matter is, because this is a general result, for any field it will work. But if you want to have an example, so consider, for example, a point particle and draw a circle around it. Okay?
I understand why it would work for that. But I feel more complicated electric fields, it looks like it shouldn't work.
That it shouldn't work.
Yeah,
Okay,
if I have a sphere and I draw a path, that half that's inside the sphere, half that's outside.
But I mean, since we did a mathematical proof, that it works, right. So we know that it's.
I'm trying to visualize it.
Huh? Yeah, that's a more difficult thing. That's yeah.
It's because you have 2 different electric fields. One is value 0, one is different value.
No, but what he wants, I mean, the problem is the visualization. Not everything is that easy to visualize. That's a problem. Okay. So in this case, we just prove it, and so that for our purposes is enough. To visualize for a generic field that this is going to be the case, it's a very difficult question you're asking.
So
I can come up with a very complicated field and a very complicated curve, and I don't think any human being can imagine why that's going to be zero, because it's, yeah.
So let me ask the question this way. So we're saying that if I have a charged sphere, any path, and I draw a path from one point on the sphere to another point on the sphere, there should be E dot dl should be zero.
Why is there a sphere here? I mean, there is no sphere here in the derivation. What are you thinking?
I'm just trying to think of an actual case. If I had a case, a simple case, a charged sphere. So inside the sphere has inside the sphere is electric field of zero. The outside of the sphere has a radiating outward, right? So if I take 2 points on the 2 edges of the sphere, since I can connect them on the inside, there's zero. The electric field is zero. So now if I draw any path going around in space from one path from one point into the other point of the sphere, it's also going to be zero.
No, because only right outside the edge is electric field.
No. Okay, I understand what you are saying.
There's a point where there's no electric field, but once we're outside.
Let me think.
No, there's electric field everywhere. The value of zero.
But when you're saying from your front one on the edge, even on the edge, that's still zero. Use the dx along the edge of the sphere as the charge on it.
Okay, guys, stop, because we have a lot to do, but I understand your problem. I'm gonna design a homework to answer that question. I understand what you are saying. It's good. So yeah, I understand. So I will give you homework, and I will do it myself, but it has to be zero. Yeah. Okay. Good. It's good that you are thinking like that. But let's move on, because we have a lot of stuff to do. Okay. So now everybody is in agreement that if we do the integral from a to b on the bottom, it's going to be equal to the integral from a to b on the top, correct?